Hello, everyone. I'd like to begin by asking you to imagine a different way of building intelligence in space. What if, instead of making each satellite smarter in isolation, we enable an entire constellation to learn as one through a decentralized architecture? Well, this is exactly the vision I'm going to walk you through during the next few minutes. My name is Ruxandra Tudose. I'm a master's student at KTH in Stockholm, Sweden, and I'm also one of the co-authors behind a paper entitled Communication Efficient Learning for Satellite Constellations. Throughout the past years, we have seen a significant surge in the number of satellites that orbit around Earth. These satellites produce massive amounts of data in an environment that we know is limited by bandwidth. As a result, data never gets transmitted, or even worse, is overridden due to the limited storage that we have on board. In addition to that, we have recently seen a trend in a need for privacy-preserving cooperation across satellites. All these requirements and this context has led to the following question: how can we enable cooperative learning over satellite constellations under strict communication constraints? Well, our solution: deploying federated learning, which is a decentralized machine learning paradigm in which the raw data never leaves the device, only the model updates. And more precisely, as part of our solution, is the algorithm under research, FedLT-SAT, which was developed at my home university at KTH in Stockholm, Sweden. How does this work? Well, each satellite in the constellation taking part in training will run the model for a number of epochs. Upon the finishing of these number of epochs, the model updates are compressed and sent to the server. The server can be either a ground station or another satellite in the constellation. The same thing will happen on the server side. We will aggregate all model updates from all satellites taking part in training, and then compress and send back the aggregated version of the model. In order to make up for the limited bandwidth, we compress, but at the same time lose data. To make up for this data, we will also employ error feedback to always keep track and add to the next round what has not been sent. This way, we try to preserve model accuracy as much as possible. So how feasible is this scenario, you may be wondering? Well, we have run simulations in an environment called FlyStack, and our simulation included 100 LEO satellites with 10% participation in training. And the results? Well, compression can be found under different settings. We chose 4 to study. We looked at compression under the form of quantization with high precision, quantization with low precision, as well as sparsification, first with 80% of the parameters being sent, and then with 20%. We have computed the asymptotic optimality error for FedLT-SAT, the algorithm developed at KTH. And as we can see, in 3 out of the 4 scenarios, it showcases as the best solution when compared to the state-of-the-art algorithms. To conclude, I'd like to stress that FedLT-SAT enables communication-efficient onboard learning. And by using this architecture, we move from isolated satellites and isolated intelligence to shared constellation knowledge. And of course, if you're more interested in finding out more about the paper, you can scan the QR code or alternatively look up the following link. Thank you very much for your attention.